first of all, I'm going to take questions that you guys might have had on the homework, and also make an observation here. Yes?
So for the first ones, 31 through 34, I knew how to do it once I got the signs and like once I got the points, I was fine and I knew how to get those. But I didn't know how you got 3 pi over 4, like how you got the actual coordinates for any of those.
Okay. Well, here's the thing. At this point, when we're doing like number 31, basically what you're going to have to do, because we don't have that part of the unit circle yet, you would have to then use the calculator. Alright, so making sure that you're in radians, because that's 3 pi over 4, it's in radians. You would just do 3 times pi divided by 4, and then just punch in sine. Okay, sine is 0.707, and so on, which you might recognize from what we did with the unit circle as radical 2 over 2. If not, it was fine if you used the 0.707.
Oh, okay.
And then if you did the same thing, 3 times pi divided by 4, and you did the cosine, you see you get a negative 0.707. Once you get those two, the rest you should be able to just get. Okay.
Yeah, my brother, he did the unit circle for me and he showed me, but I didn't understand how we would do it if we didn't have a unit circle.
Okay. Yeah, you just had to use your calculator to do the first 2, and then you could get everything else from there.
Okay.
Yeah, Brett?
What if you just forgot about the 3 and 2 pi over 4 and used those coordinates?
Well, that's kind of what you end up doing. Pi over 4 is what we call a reference angle, which we're going to get to. The only thing with that is, you might notice here, cosine ends up being negative.
Yeah.
And tangent ends up being negative. And that's because this angle here is in the second quadrant. Okay? The only thing that is positive in the second quadrant is sine, and then of course cosecant, because it's just a reciprocal. But that's how you do that one. Now, looking back here at 1 through 4, I know you only had to do 1 and 3. But you'll notice they gave you angles, 1 in each quadrant. Okay? It would have been nice if they had given you a 1, 2, 3, and 4. That would have made a little more sense, but whatever. But you notice over here, if we make a right triangle like this, and then we look at this angle, since it's kind of the one that is closest to the theta, in fact, it's the supplementary angle, right? Then you can use the coordinates of the points. Given that this is a unit circle, we have a negative 8/17 here, and we have a 15/17 over here. So you automatically know that the sine is which of those?
15 over 17.
It's the y coordinate, 15 over 17. Alright? So sine, put it over here, is 15/17. Cosine is good, negative 8/17. And then tangent is what?
15.
Yeah, 15 over negative 8. Negative 15/8. Okay? So you see what ends up happening is here in the second quadrant, the only thing that's positive is sine. Okay? Both cosine and tangent end up being negative. Now, look over here in the first quadrant. what's going to be positive in the first quadrant? All of them. Okay? All of them. So it's a positive sine, a positive cosine, a positive tangent. Okay? Over here we had a positive sine, negative cosine, negative tangent. What about over here in the fourth quadrant? What do you think? Which one is positive? No? In the fourth
Oh,
quadrant?
the fourth quadrant. Oh, that's sine is negative, tangent is negative, cosine is positive.
There we go. Sine is negative. Cosine is the one that's positive because the x-coordinate's positive. Alright? But since sine over cosine would be a negative over a positive, that means tangent's also negative. Okay? And then what do you think is going to happen in the fourth quadrant? Okay? Tangent will be the only one positive there. So both the x and y coordinates are negative, so sine and cosine are negative, but a negative divided by a negative is going to give you a positive, so that's how we get a positive tangent. Okay? Yes?
Just out of curiosity, are we going to be completing the inner circle in this unit?
Yes. Now, do you see a pattern? Which trig functions are positive in the first quadrant?
Sine.
Sine is, cosine is, tangent is, so they all are, right? In the second quadrant, what's positive?
Sine.
Sine. In the third quadrant, what's positive?
Tangent.
Tangent. In the fourth quadrant, cosine. Okay? Cosine. So this is a little picture that you're going to probably end up writing at the top of most of your papers every time you do stuff with trig. And that is this. That little thing right there will help you remember what's positive in which quadrant.
Jamie Pizarro, please come to the 400 building. Jamie Pizarro.
So, what we have there, again, a real simple way of remembering what's positive in which quadrant. An easy way to remember it, since we rotate around this way, all students take calculus. That's a little way to remember where they go. Because it's first, second, third, fourth quadrant, so all students take calculus. It's just an easy way to keep it straight, whether or not it's true. Okay? Any other questions from the homework?
73.
What's that?
73.
73. Let's see, that's the electrical circuits one.
I don't know that.
Okay. Let's read this one together and we'll figure it out. Okay? The initial current and charge in an electrical circuit are 0. The current when 100 volts is applied to the circuit is given by I equals 5e to the negative 2t times the sine of t, where the resistance, inductance, and capacitance are 80 ohms, 20 henries, and 0.01 farad respectively. Okay? Approximate the current in amperes, t equals 0.7 seconds after the voltage is applied. Right? Well, here's the deal. This is a great example of a lot of worthless information when it comes to solving our problem. Okay? Because the only thing that really matters here is this and that. Okay? What is the current That's I. Alright? What is the current when t equals 0.7? Alright, so there's a lot of words and a lot of things that we've probably never even heard of before, but that's okay, because none of these matter. Right? All that matters is, here's our equation, here's the time we want it at, so I is going to equal 5 times e to the negative 2 times 0.7 times the sine of 0.7. Okay? Now, it does not say this here. Okay? But make sure your calculator is in radians.
Why?
Why?
Okay? Well, because most of these formulas, and I think the book says it somewhere in there, most of these formulas rely on when you're using sine or cosine or something like that for it to be in radians. Okay? What page was this again? 274, 275. Okay. Alright, so there it is. Okay. It says for 71 and 72 that it's in radians. Okay. I think they mentioned it at some point here, but I'd have to find it. But when in doubt, and especially if it looks like something like this, I think they're relying on the fact that they did not put a degree symbol in there. Okay? If they wanted you to use degrees, I would think that they would put sine of t degrees. Okay? So if you don't see that, or you're not told otherwise, if you have to guess one way or the other, use radians. Okay? Yes.
So for the test, will you expect us to know or to figure out which one to use?
I'll make it clear.
Or make clear?
I'll make it clear which one I want you to use.
Okay.
So. Alright. So, whatever that value actually is, did someone find it?
0.794.
0.794.
3
Ampere.
1 1.
Okay. And this would be in current in amperes. Yeah. Alright. So that's how you'd find it. That one is actually a whole lot easier than it looked. You just had to wade through all the extra information that they were giving you.
I just wonder how the answer got 0.25
Oh, I don't know.
on the book.
The book got 0.25?
Yeah. I think probably the book used radians.
Wait, did you guys, when you got this, did you use degrees or radians? You used radians? Let's see here. We have, if I were doing it on this calculator, I'd have to do -2 times t, so 0.7, and then I need to do e to that power, so -1.4, so e to the -1.4 power, now times 5, and then times the sine of t. Alright, so I'm going to put in times 0.7 sine equals would be 0.794.
Do you want me to try it in degrees?
You get 0.015.
In degrees, you get 0.015 times 5 times e to the, it was negative 1.4. Yeah. Yeah, either way you do it, you're not going to get 0.25. So, I'm not sure which one you were looking at, but. Alright, or they may have just had a typo or something in the back. Alright, so what I want to look at today is actually start kind of building off of what we've done so far. And we're going to start looking at some properties of the sine and cosine curve, or sine and cosine as functions. And then we're also going to look at how these functions are related to each other in different identities. All right, now we've already looked at a couple of identities. We saw the reciprocal identities, where sine is the reciprocal of cosecant. Okay, cosine is the reciprocal of secant, and tangent is the reciprocal of cotangent. So you've seen those before. We also talked about the quotient identities. Tangent is what over what? Good, sine over cosine. And it would follow then that cotangent would equal cosine over sine. All right? So, believe it or not, you actually have all but 3 of the main identities that we're going to use. Okay? But before we get to those 3, I do want to look at the sine and cosine graphs and talk about the concept of a periodic function and amplitude and period. And the reason why we're doing this is to kind of tie together what we're doing with the concepts of coterminal angles and some of the other things we've talked about. All right. Now, I sketched for you here the sine curve, and you'll see we start at 0, and then it goes up to 1, and then back down to 0, then down to -1, and then back up to 0. Then it goes up to 1, and down to 0, and -1, and up to 0. And then it just keeps repeating that pattern forever. If we kept going to a positive x side, we would keep going. If we went to the negative x side, it would continue that same pattern. All right, and that repetition, an exact pattern repeated over and over and over again, is what makes sine what's known as a periodic function. Now, you'll see here I kind of divided this with these red lines into 2 separate periods. All right, so this right here is a period. Here's another period where we have exactly the same thing. Okay. Now, for sine, the period is 360 degrees, or 2 pi if we're in radians. Now, if you think about our unit circle, that makes sense. Okay? Look at our sine, which is the y-coordinate. At 0 degrees, we're at 0. Then it goes to 1, then 0, then -1, then back to 0. And then we're just going around the circle again. And we can keep going forever, but we're still going to have the same values no matter how many times we go around that circle. Okay? That's because the period is 360, or 2 pi. Now, with that being said, what would the domain of sine be?
X.
X is
Oh,
0,
that's
1, and 1.
A number of you are saying -1 up to 1. That's not the domain. What's that?
That's a range.
That's the range.
What?
Oh,
Remember
yeah.
to say that?
What?
Greater than 0.
No.
It can be.
Infinite? Infinite?
What do you say?
Infinite?
Infinite.
It's what would we say then? From negative infinity to a positive infinity, that would be all real numbers. Okay.
So give me that.
Yes, you can take the sine of a negative angle. That's why we have it rotating clockwise. You know, you can get negative angles. Okay? So this continues on in both directions forever. However, our range, like some of you already said, goes from -1 up to +1. Again, if you look at your unit circle, we never get bigger than 1 or lower than -1. Okay? So that's related to a concept we call it amplitude. Alright, you'll notice here that our sine curve has kind of this middle line. The x-axis is kind of that middle line. And our amplitude is going to be the distance above and below that midline that our graph takes. Okay? Another way of thinking about your amplitude is that it is half the distance between your minimum and maximum value on your graph. Okay? So if our minimum value is a -1 and our max is a +1, what's the distance between those?
0.
A distance.
Oh,
Oh,
2.
2, so half that is
1.
1. Alright, so our amplitude is 1. Okay? And that's not going to change unless we were to multiply sine by something, and we're going to do that later on. But our amplitude will equal 1.